Good morning, good afternoon, and good evening, everyone. So today we're going to be continuing our Applied Linear Algebra series, and we're going to proceed to Lecture 3, which is about vector spaces and bases. So in the previous lecture, we introduced linear combinations of a set given a set of vectors. And so let's say we have a set of vectors v sub 1 to n in Rd or in d dimensions. And we have this vector w where if we add up all of the vectors in our set with some scalars, then we get that vector w out of it. And so we say that if the alpha j's are all 0, then our vector w, the output, is going to be a trivial linear combination. It's going to be an obvious linear combination of the vj's or of v1 to n. However, if any of the alpha j's or if any of those scalars are not 0, then we say that W is a non-trivial linear combination of the VJs. And from there, we defined linear independence. So linear independence is assigned to a set. So it's not about the vectors, it's about the set of vectors. So given a set, V1 to Vn, we say that the set is linearly independent if we take this sum of a bunch of scalars with all of the vectors in that set, we equate it to 0, and we see that the only solution is that when all the scalars are 0, then we know they're linearly independent. So if we actually go back here, we can actually define which one of these are linearly independent and dependent. This thing, this statement here, this is independent because all the alpha are scalars are 0. So this is an independent set from V1 to Vn. And you guessed it, we can say that this other guy here is a dependent set containing V1 to Vn. Cool. Okay, moving on to vector spaces. So the operations of addition and scalar multiplication that we have defined for d dimensions imply it as an instance of what we call a vector space. So in mathematics, a space is a set of elements that follow a certain set of rules and properties. So this is very, very abstract. So we're gonna go through this bit by bit. So a vector space, in this case, right, is a collection of elements. When we say collection, that's another way of saying set. So it's a set of elements for which scalar multiplication and addition are defined in such a way that the result of these operations also belong to the same collection. What does that tell us? It actually tells us something about linear combination, right? Let's actually apply that right now, what we just learned. Let's say this W. Here we have a set of vectors V1 to Vn. And we did vector addition with V1 to Vn. But we also did scalar multiplication because we multiplied alphas to each of these vectors. And we get this vector W out of it. So what does that say? That tells us that W is also part of that set, that same set. Or in this case, all of these vectors are in the same vector space, right? But it's really just logical reasoning. Okay, so they belong to the same collection, so same set, right? Okay, why is this not working? Same set. And these operations satisfy certain rules. So here are the rules. More precisely, so to be more mathematically precise, we denote vector space as capital V. If it's closed under addition, so here are a bunch of properties, right? Say we have vectors u and v, and we say that they belong to this vector space V. Then when we add them, it should also be in the same vector space. And then same idea, commutativity. That just means when we add vectors, we can reverse them and they produce the same thing. And we also say that they are part of that same vector space. Then we have associativity. So this is when we're given three vectors and we can add any of them in any order. And again, they all belong to the same vector space. So you're just doing a bunch of addition to those vectors. Additivity. So here there exists a zero element. So this is what we call a zero vector. It just has a bunch of zeros all the way to d dimensions, right? Such that when we add some vector u to zero, it's just going to be that same vector u. And that goes for all u in v. So this is another weird looking notation. This just means in English for all belongs to. And then v is the vector space. Okay? Cool. And then we have additive inverse. This is for every u vector in that vector space V, there exists. So pretty sure I did talk about this notation here. There exists, or there is a vector negative. We just put a negative, and we also say that that negative vector u is also in the same vector space as the original one. And so when we add those two vectors together, we get the zero vector. And that pretty much makes sense for addition, right? When we subtract the same number from a given number, it's just going to be a zero. 5 minus 5, 0. 4 minus 4, 0. 1 million minus 1 million, 0. So same idea, but this time with vectors. And then we also have, so that was mostly addition, right? What was this, Roman numeral? 1 to 5 is mostly addition. But now we go to multiplication. So say we have a scalar alpha, u vector belongs in vector space V. Then when we scalar multiply the two, so we multiply alpha to vector u, then that resulting vector is also going to be in the same vector space. Distributive, okay, there's a bunch of them actually. Alpha, beta are real numbers, and u and v are in the vector space. Then all of these, so yeah, all of these are going to be in that same vector space. But this is just distributive and associative, right? This is pretty self-explanatory. And then these ones are just special stuff. So we just multiply u by 1, we get the same thing. Multiply u by 0, we get 0, because anything by 0 is 0. So that one still applies to vectors. Negative 1u is just negative u. And we all assume that all of them belong in the same vector space. And we have a couple of properties that we can look at, right? Right. So that's where I stopped taking notes. Well, for one, it's nighttime during that time, so I need to take a break. But now let's actually quickly check that RD satisfies these properties. Okay. So we're going to check if RD. So I'm pretty sure we're going to try proving some of these things, if that makes sense. If not, bear with me. So we say, okay, we have U, we have V, and what we can do, right? This one we've seen a lot of times. Or no, we've seen this in lecture one, not a lot of times. I've seen it a lot of times. So, okay, why is it not working? What I've also seen a lot of times is my OneNote is not working. And now, okay, yeah, it crashed. Okay, U sub 1, V sub 1, all the way to U sub D, V sub D. Right? So we just add their respective components. So this one again was our vector addition. Okay, it's not working. So that was our vector addition, and this is our alpha. This is our scalar multiplication. Okay. So what does this tell us? These two ideas based on the properties. When we add, say, two vectors, this is still in RD, remember? Because again, we're just adding the components, so we're still gonna get the same number of components. And so what does that tell us? This tells us that this is actually closed, or this has to be closed under addition, which is one of the properties we just talked about like minutes ago. And then we have the scalar multiplication, which again also belongs in RD, right? Because again, we just have the same number of components. So this is also closed under scalar multiplication. Scalar mult. So these properties are from 2 and VI. See if I guessed that right. VI. Oh, I didn't guess it. It was I. I don't know why I wrote 2. Okay. So that was that. There are some ways of proving that all of these are true. I'm not going to prove them anymore because that sucks. So, uh, okay, yeah, he proved. Okay, my professor proved everything. That's why this took so long. Okay, we don't need to prove these. We already know how this works. Right, now here, okay, this is where it starts to get a little interesting. Let's look at the definition. The thing about definitions, at least in this class, it's really gonna throw you off the first time you see it. A subset? Holy moly, what's a subset? Now we know what a subset is, right? Hopefully. Say we have a subset W of a vector space. So remember how I said a vector space is just a set? So what does it mean to be a subset? Okay, I'll give an example, just to be clear. Say we have this set. We have 1, 2, 3, 4. That's a set. What can a subset of this be? Maybe a subset could be all the even numbers from this set, so 2 and 4. Maybe a subset could be all the odd numbers. Maybe a subset could be 1 and 4 for no apparent reason. So it's basically just a part of a set. That's what a subset is. So it's a part of a vector space. I hope that makes sense. So a subset W of a vector space. Yeah, here in math, they like to put letters on everything just to make it more formal, I guess, more defined. So vector space V is what we call This one you're gonna hear this. A subspace. See how original that is? From set, we turn it to subset, and then from space, we turn it to subspace. Yeah. Mathematicians give very original names. I'm being sarcastic. If it is itself a vector space, if it is itself a vector space. So a subspace or a subset can only be called a subspace if if it is itself a vector space. So maybe an example, say we have this vector space which contains, I don't know, v1, v2. I don't know what components there are, but these are vectors, right? So maybe a subset could be w is equal to v2. And this is still a vector space, right? It's just a subspace of v. I think there was a way to write it like that. I'm not sure. I forgot how to write it in mathematical notation. I'll learn it along the way. Doesn't matter. So when we say that it is a vector space, then it has to be two things. It's closed. So this one we've pretty much discussed. It's closed under addition, and it's also closed under scalar multiplication. What that means is, again, if we add it, we add two vectors in that same vector space, then the sum of those two vectors is also another vector that's in the same vector space. If we multiply a vector, but that vector is in the vector space, then the other vector that we multiplied with, a scalar, is also in that same vector space. Or if we combine these two, we add some vectors, we multiply them by some scalars, that vector in it of itself is in the same vector space. Okay? I hope that makes sense. If not, you can roast me. So, okay, let's do an example real quick. So say we have the set the set of vectors. So let's do W. So this is W is an R2. So it's actually a vector. Such that, uh-oh, is my thing not responding? Okay. Such that W is equal to W sub 1, 0. This thing, oh my goodness. My OneNote not responding. So this W vector is a subspace of R2. I hope that makes sense. Right? What else can we say? W sub 1 is a number. Okay. Okay, so we have this set, right? What can we say about it? So clearly, every W in this set W, capital W, also belongs to R2. Okay, I hope that makes sense. So if we're given some vector W in two dimensions, but we say that this W has only a zero component, uh, second zero component, its second component is 0, then it's actually just all of the W's with the second component being 0, that's part of the subspace W. But this is also part of R2, right? Because R2 contains all the vectors that the set W contains. So that's why we say every small w in that big W also belongs to R2. So what that means is all of these W belongs in R2 as well, right? Okay, let's try this out. So we can actually say W is a subspace of R2. That's what that means. Okay, so also, here's another idea. Can't, oh my goodness. Yeah, my OneNote is bugging. For some reason, every time I switch tabs, because I'm also looking at the lecture notes while I'm doing this, just so you know. Oh no, I read, my bad, NW. So let's say we have U and V and they're in that subspace W. We have, say, alpha. We multiply it to U. And let's say that's equal to uh, alpha U sub 1, 0. What does that tell us about this vector here? Again, it tells us it belongs to the W. Why is that? Because the second component is 0. And that's what this rule is telling us. We we have a second component that's 0. It's actually just part of W. Set W, or the subspace W. So that's what that is. And another thing we can say is, well, so say we already have that alpha U, and we have this V. When we add these together, we would get something like this. Or to be more specific, with the second component, we'll probably get, okay, this OneNote is bugging me. Okay, now it's deactivated. Oh no, it's not. Right? 0 plus 0. And this belongs to W. Right? We just added these two vectors together, so they should still belong in W. Okay, we have a couple of stuff here. Oh, okay. So here's the fun part, I think. Actually, I don't think this is fun. Really, I don't like proving too much. I think it's annoying. But if you're someone who likes proving, nice. I'm gonna show you that right now. So here's my claim. So I claim that given any collection of vectors, okay, let's say, why is this not responding? Vn in Rd. So we have those collection of vectors, right? Now we're gonna go back to this idea that might throw you off, but we've seen it. But I'm guessing it's not clear. Span of the same set of vectors. So what am I saying? Span is actually a subspace of Rd. That's my claim. So I'm pretty sure you guys can somehow connect the dots, but I'm gonna write a proof on it. So here's the proof, or here's why. say we take any W and we say that W is part of the span of V sub 1 to V sub n. Then what does that mean? If it's part, then that means that W can be written as a linear combination. Okay, we've seen this, right? Hopefully, of alpha j vj. And we say that this resulting vector is also an RD. We don't have to explicitly say it, but we just say that everything here is an RD. But that's the idea. We can write it as a linear combination because it's part of the span. And so actually what this means is that these vectors are linear, or no, the set of these vectors are linearly dependent, right? Okay, also, so here we say, I'm gonna add a new letter, might throw you off. Beta times this W vector. This is a different scalar. That's what I'm just trying to say. So we do a summation here, and we do, uh-oh. I think I keep opening random stuff. Okay, so I do a summation here all the way to n beta times alpha j bj. Oh no, so it wants me to multiply this thing first. So here what I basically did was I multiplied this equation. Oh, oh no. Somehow this is bugging. I multiplied this equation by beta on both sides. That's what I did. Now, what does that have to do with anything? You'll see. But what this tells us is that this beta W is still part of the span. Because we just multiplied, we just scaled it. That's what happened. Okay, that makes sense. Okay, I think this is the last bit. Finally, when you hear the word finally, you're gonna be happy. This is the last bit. We again have a new vector that's part of the span of these guys, V1 to Vn. And so what does that tell us? That tells us that U can be written again as a linear combination of these vectors V1 to Vn. What symbol do I use? I'll use this symbol. Bunch of symbols, but they mean the same thing, right? Then we say U plus V is, oh no, U plus W, my bad. Oh, now we're combining these. So we're actually just using the idea of linear combinations for the most part. And if we can do that, then that means they're part of the span. So this is, when we add those two together, well, that just basically means we're adding what's in U and what's in V. So I'm going to shortcut this, but this plus this. So it's actually the same thing as alpha j plus this symbol j, vj. And what can we say about it? Again, this is part of the span of v1 to vn because we're just adding it. So technically, we're treating the span as a subspace. So the span is a subset of Rd, and we say that the span is closed under addition and scalar multiplication. I think we do a QED here. We're done with the proof, or semi-proof. Cool. Okay, we are close to done. Not really. I'm kidding. We're getting there. Now we go into some other definitions of more abstract ideas. Man, I enrolled for this degree applying math, not proving stuff. But anyway, I mean, that's where it all starts, right? You prove something, then you apply it. So let's say we have this subspace. Okay, yeah, that's how you write it. So say we have that subspace V that's NRD. But it's not like a collection of, it's more or less a subspace. That's what that's telling us. And a set of vectors. Okay, next time I'm actually gonna write the set itself. Uh-oh. And these vectors are in the dimensions. So here we say that all of these, so the VJs, they actually just span subspace V. That is if every vector in V can be written as a linear combination of the VJs. So what does that mean? So say we have, okay, let's take a pause for a second. We have a set of vectors v1 to vn, right? They're in d dimensions. And then we say that the VJs, they span V, or they're part of the span of V. And V is again just a set of vectors, right? They span V if every vector in V is a linear combination of the VJs. So what is that? Like, what in the world is that? Say we have this set, V1, V2, V3. This is a set, right? We say that the VJs, V1, V2, V3, they span V. So their span is equal to V if every vector in V, so what does that mean? Every vector in V, say V, okay, let's say V has W1, W2. That's the set that V has. Can be written as a linear combination of the VJs. So we say that maybe V1, W1 could be V1 plus V2. Then we know this works. Another idea, W2 could be written as V3 plus V1. Another idea, W could be written as V1, V2, V3. W2 could be written as negative V1 plus 5V2. This is so random. Minus 100 V3. But the idea is if we can do something to these V1, V2, V3, we play around with addition, vector addition, scalar multiplication, subtraction. then we get somehow we get W1 and W2. Then the span is equal to V, right? That's what I'm trying to say. Okay, why can't I? Mhm. Uh-oh. Okay. I thought it was gonna take forever to load. Man, this thing's taking forever. VJs. So yeah, that is the span. Okay, I just wrote it, but the textbook's writing it again. Span of these vectors is just V. We can even say, yeah, we can say that if we are able to write a linear combination of the VJs and get some vector W out of it, then that vector W is also part of the span. So we could also do that. Okay. So okay, maybe to be more concrete, let's do a numerical examples. So I just said is numbers. We're gonna do numbers. Numerical examples. Okay, we have 1, 2, 0. We also have 2. Throw a pi in there. Why not? And what can we say? We say that this span is equal to this span. 5, 6, 0. What's this? Square root 2, 1, 0. Then maybe 100, 1 over 3, 0. So the span of those two things are equal. Why is that? Technically, these are all vectors in R3 because they have 3 components, so they have 3 dimensions, whose third component is 0. Okay, now here's the new thing that we're going to look at. So definition. Uh-oh. So we say that set of vectors. Uh-oh. Okay, I think the OneNote is completely done. So we say that this set of vectors that belong in RD. Oh my goodness. Ah, it anyway. So we're talking about the set, right? Not the vectors. We say that the set is a basis for a subspace. Let's call it V in RD. So notice here I'm using a different notation for subspace. If the VJs are, so one, they're linearly independent, meaning you can't write a linear combination of one of them among the rest, based on the rest. And we can also say that their span, the span of this set of vectors is actually just V. It's the subspace. The span is the subspace. Then we can say that they are bases. So let's actually give an example to concretize what we just said. So let's say we have this set, right? And I think this one's an easy one. So say we have that set of 3 vectors. What do we notice? These are the standard basis vectors. So the set is actually a basis for what? R3. So the thing apparently that we've been discussing in Calculus 3 has now been connected to here. Now we know the reason why they call it standard basis vectors. Because each of these vectors are linearly independent, right? You can't write one of them as a linear combination of the other two. And, well, their span, the span of the set of these vectors, is just R3. How do I know? So there's this rule that if we somehow, so this is in conceptual linear algebra, if you turn this into a matrix, where a matrix is just a column of vectors, and you see a pivot in every row, then you know they span something. There is a pivot every row. But that's not what we're going to do here. I haven't talked about it yet. Or at least it might be different for this course, but we'll see. There's a big but. Big but, the vectors, just say we have 1, 0, 0. We have 0, 2, 3. We also have 0, 4, 5. Then we have 0, 1, 0. How about this set of vectors? These are not a basis for R3. Why? Let's check. Are they linearly independent? Actually, I don't know. I have to check it myself. So we could do the alpha technique. Could we write one of them as a linear combination of the other? Something I also have to check. Can't eyeball it. I don't think so. Oh, even though they span it. So we can actually say that they span R3. Because if we convert this into, okay, if we convert this into a matrix, we do row reduction, and we're able to get a pivot every row. So they would span R3. But they wouldn't. Oh, okay, so they're not independent. I see. Hmm. Look at that. Apparently, one of the vectors, so we use the first definition here, or at least the lecture used a definition here, is actually a linear combination of two other ones. And remember, if we can write one of them as a linear combination of the others, what does that mean? That means there's a dependent set of vectors. Oh yeah. Finally, I love that word. Okay. Finally, so say we have the set of vectors. Okay, I'm gonna throw in a pi there, why not? How about these? Is this a basis for R3? It's not. Why? Why is it not a basis for R3? Well, okay, this one we can kind of eyeball it. There isn't a pivot in the third row if we convert this to a matrix. And if there isn't a pivot in the third row, or if there's no pivot in every row, then that means they don't span. R3. Okay, cool. What else? What else? What else? What else? So, nice consequence of having a basis of a subspace is that we can represent every vector in that subspace as a unique linear combination of the basis vectors, right? Okay, another proof. Ay, ay, ay. Actually, let me just write this out. We're close anyway. So, a nice consequence of having a basis for a subspace is that we can represent every vector in that subspace as a unique linear combination of the basis vectors. Okay, here's my claim. My claim is that, say we have, consider a subspace D in D dimensions. So this is a very general statement. And a set of vectors. Oh, let's be specific. Basis vectors. So when we have basis vectors v1 all the way to vn, what does that tell us? It tells us that these vectors span the subspace V. Their span is the subspace V, and the set is linearly independent. And we can say a lot of things about sets of vectors that are linearly independent, such as we can't write one of them as a linear combination of the rest. Or if we put alphas, we scale them by alphas, we add them together, they equal to 0, then we only have that trivial solution where all alphas are 0, right? That's all ideas popping out of our heads right now. Okay? So these guys span V, the subspace V. Then any vector so this one is just any vector U, let's do W actually. And let's say that W belongs in the same subspace V, can be written as actually just a linear combination of the rest of these guys, right? For a unique set of, did we say vectors? No, unique set of scalars. So that means they're not all 0, or they're not all the same. Alpha 1, alpha n. Now, what can we say about these scalars? another new thing here. These, I already said it, kind of. These scalars, so when you have basis vectors, what do you call these? Call these basic coefficients of this W vector. Okay, let's do an example. Try this out. So say we have the basis, a set of basis vectors. So it's going to be a set. And we already know what this is. Standard basis vectors. What is this? Okay, let's assign it. I'm going to do it very informally. I'm going to say this is V1, V2, and 3. So I don't have to write all of them again and again. And we say we also have another vector W, which has components 3, 4, and 5. So you can actually write W as a linear combination of the rest. 3v1, 4v2, and 5v3. Right? And so what do we say? What can we say about this? We say that this 3, this 4, and this 5 are what we call the basis. Oh, I wrote basic. Basis coefficients. Ah, uh-oh. I did not mean to write it in that. Okay. These are the basis coefficients of W. Okay. Do we have other examples here? Actually, no, this is the last one. Let's actually just do this one. And then we can call it a day. So let's consider this set here, which has 210, 110. And then we say that this is V sub 1 and V sub 2. And let's say this is a basis for a set of vectors in R3. Okay? With 0 as the third components. Then this W, say we have 4, 5, 0, can be written as alpha 1, V1, alpha 2, V2, which is equal to W. Now we find these alphas, right? So we can actually just convert them to a linear system. It's fine. I don't want to do any more linear algebra stuff, but so we just multiply 1 is equal to 4, alpha 1 times 1, alpha 2 times 1 is equal to 5. And then solving it, well, we would just get alpha 1 to be -1, alpha 2 to be, for sure this was 6, and we're done. You can write W as a linear combination of V1 and V2. So we say W. Okay, I'm going to finish it off. negative v1 plus 6 v2. So W is, well, for one, part of the span of v1 and v2. And since, what can I say? Oh no, they already are bases. So W is part of that span. So we're gonna say span and W is actually just, shoot, my bad. No, they're not R3 because they are dependent. Actually, no, that was right. Yeah, they probably should have a pivot in every row. I'm not gonna be surprised if they have a pivot every row. Okay, so that's all for this video. I hope you guys enjoyed this long lecture. So just to tease what we're gonna do next. I can't. Here's what we're gonna do next. Okay, there's nothing here. Let me go look at this lecture. So in lecture 4, we're basically gonna talk about, so we talked about subspace, but we haven't talked about dimensions of a subspace. And we're gonna introduce this new thing, but I think for many of you who have been watching my calculus series, this is not something new. How this relates to inner products. Same thing, we've called it dot products. Okay, so that's it for this video. I hope you guys enjoyed, and I'll see you all in this next lecture.